Hello, everyone. Welcome back to the AAS YouTube channel. And this one is going into the AAS Author Series. And I'm very happy to have Grzegorz, oh God, Grzegorz Kowal. There, I got it. I got it.
Yeah.
Sort of got it. My apologies for butchering that. How you doing today?
I'm good. I'd like to thank you for the invitation, to talk about my paper.
Well, I think it's a lovely paper.
Well, I hope so.
So where are you located at?
I live in São Paulo, in Brazil, but I'm not Brazilian. I'm Polish. I came from Poland. I came from Poland, and like 11 years ago, maybe I moved to Brazil to start doing some research, one of my postdocs, and then I settled down here, and right now I have a permanent position here, and
oh, great!
So my life is going on here in São Paulo.
Awesome.
Yeah.
Cool. And how are things pandemic-wise in São Paulo?
It's difficult. Of course, Brazil is the second one in the world, and it seems it's not stopping. It's not slowing down, but since my wife works in a hospital, she has the direct contact with the patients, and she said that the situation, at least in the most difficult cases, is improving. So this is somehow a good sign, right?
Yeah, yeah.
Yeah, but probably it will take a few more months before the situation comes back to normal.
Yeah, we are. I think the U.S. is in the same boat. It's going to be a few months minimum. So we shall see. So what do you like to do for research?
I usually work with simulations, numerical simulations. I do simulations of plasma physics, some applications in astrophysics. My usual topics are turbulence, magnetic reconnection, particle acceleration, all the stuff which is important in astrophysics to confirm observations, to explain the observations, but I am not directly an observer. I have some history to work closer with observers and to confirm our, for example, theoretical predictions, and it was very nice collaboration. So I think this relation, this experience between different communities, scientific communities, is very important.
Oh, definitely.
Mm-hmm.
Very cool. All right. Well, with that, let's go ahead and get into this lovely piece of work. So we're going to share, and we are going to go over statistics of reconnection-driven turbulence.
Yes.
Grzegorz, take us away.
Okay, so thank you for choosing this paper. It's a relatively recent paper, like 3 years old paper, but it's not some kind of independent work. It's one step in our big project of turbulent reconnection, I would say. So, of course, I am not working alone on this project. We have several groups in the world collaborating, and each one does some particular stuff related to this turbulent reconnection. And just to give some introduction, reconnection is very important, of course, in the astrophysical plasmas. We have plenty of astrophysical environments which are magnetized, and of course, if we have a magnetic field there is no way we don't have also such processes like reconnection. There's another thing that because of the scales, those environments have, they are very big compared to plasma properties, the scales at which the plasma microphysics have. So there is no chance that turbulence is not existent there, you know. In all those environments, astrophysical environments, we can confirm that we have plenty of turbulence. So connecting these two parts, magnetic field and turbulence, we end up studying reconnection. A few years ago, it was shown that reconnection is independent. It's like an intrinsic part of magnetized turbulence. This work was published in, I think, 2016 by Grzegorz Kowal. And since then, we cannot say simply that reconnection is something a process which does not is not that important, or it's important only in specific environments such as solar flares in solar physics, for example. But we observe magnetic reconnection also in solar wind, in magnetosphere. We observe reconnection, maybe not observe reconnection, but I would expect that reconnection takes place in interstellar medium. Sure. And we have strong evidences that it's also important that in those relativistic objects like active galactic nuclei or gamma ray bursts, which can explain those gamma blasts. So, and of course, the reconnection is important for particle acceleration and the explanation of the highly energetic cosmic rays which we observe.
Right.
So yeah, in some sense, this paper maybe it's focused only on turbulence and the relation between turbulence and reconnection, but it can affect other areas as well, other related areas as well. So just to give some very brief introduction of the reconnection, reconnection was recognized as a process in 1950s. The first model of magnetic reconnection was introduced by Sweet Parker, 77, 78.
Right.
And this model, however, turned out to be not very efficient, I would say. It simply says that we have the large-scale magnetic field inflowing into the diffusion region, and this magnetic flux, which inflows, undergoes the process of reconnection, the change of topology, and is ejected along this very thin layer, which we call outflow of the magnetic flux. And since we have those two different scales, the very large scale compared to the size of the considered environment, and this micro scale at which the reconnection takes place, this ratio makes the model very inefficient. So since then, people, scientists, were looking for some explanation how to improve this model. We can say that this Sweet Parker model depends on Lundquist number, which is the size of the system times the Alphen speed, the characteristic Alphen speed in the system divided by resistivity. Mm-hmm. Of course, resistivity is very small in most of the astrophysical objects. So it turns out that the process described by this mechanism is very inefficient. You can easily forget about it. Just to say that, for example, in solar corona, I think it's 10 to 8. It's a this number is without dimensions. So okay. If we take 10 to 8, it divide this by, 1 by 10 to 8, it turns out that we need a lot of time to even see the manifestation of this process.
Right, and that's what you mean by inefficient. It just takes a long time.
Yes, it's in comparing to characteristic scales, it's very inefficient. Yes. So in 1999, Alex Lazayan and Itan Vishniak proposed a model. Of course, I skipped that. Since then, for example, there was another model described by Peczek, which was called the X-point reconnection, because it reduced the longitudinal scale of the reconnection to be much smaller because of the existence of the slow shocks, which could maintain this strange configuration. So it resulted in the efficiency of the reconnection process much higher. However, it turned out later that these slow shocks are only stable if we take into account the non-uniform resistivity, or so-called anomalous resistivity. So if we just deal with uniform resistivity, this X-point reconnection tends to Sweet-Parker reconnection. So since then, there was a focus on maybe finding some processes, kinetic processes, which can enhance this resistivity locally. And therefore, the communities, scientific communities which work with collisionless reconnection took over and started looking for some processes, and they could find out that in collisionless plasma, the reconnection is indeed faster. But collisionless plasma is one part, but most or some of the environments, like interstellar medium, for example, are collisional. So these effects, plasma effects, do not exist there or are not important. So in 1999, Alex Lazayan and Vishniak proposed that since we have turbulence everywhere, maybe interacting this turbulence interacting with reconnection can enhance the efficiency of the process. And indeed, they published a paper with predictions, and they found out that the reconnection is independent on the resistivity, and it's completely determined by the properties of turbulence. So nice, we had a new theory. We would have to verify it, but it's very difficult to verify it from observations. And at that time, the computational resources were limited to verify this using numerical simulations. And it took like around 10 years, so we could do this. And in 2009, I with my collaborators, of course, we did a number of numerical simulations for different parameters, for the different strengths of turbulence, for different injection scales of turbulence, and we confirmed those predictions that indeed the injection scale and injection velocity controls the efficiency of the reconnection, turbulent reconnection. And also we have shown that this reconnection is independent on the plasma properties, on the proper resistivity. So we can call this fast, you know. And one thing more is that even if our resolution was limited, and still it is, because we can go up to 10 to 4 with this Lundquist number with simulations, while in the reality it's above 10 to 8. Or in the interstellar medium, it's 10 to 15. Right. So it means that this process can be studied using numeric, right? So the model involved pre-existing turbulence in the region of reconnection. So so we have to inject externally this turbulence, but there was a question raised which asked, okay, what if the proper reconnection can generate turbulence? right?
Right.
Is it possible or not? How does it affect, if it generates reconnection, how it would affect the reconnection process, and what would be the properties of this turbulence?
Right.
So, although my paper we are discussing right now is not the first one which tried to answer that question, I should mention the work by Berezniak, 2013, who did this in incompressible periodic box. I should mention also Oishi, 2015, who did this with open boundary conditions, but they didn't focus on the properties of turbulence. And I should mention also Huang and Bhattacharya in 2016, and they, for the first time, tried to analyze the properties of such a generated turbulence. And in the paper we are discussing, we also did such sort of analysis. We allowed simply, if we go, maybe we go now to the page 7, so we can describe the setup of the model. And Frank?
Yeah.
Can you slide down to page 7?
Sorry.
Yeah.
So I did have a question. So I know you caught me because I was reading something here. You're using an adaptive mesh
Yes.
code. I guess my experience would say that if you're doing turbulence, that all you end up doing is remeshing, and you're almost better off using a uniform mesh.
Yeah, this is true, but this is true if you have a cube box and if you inject turbulence everywhere.
Okay.
And so this page 7, you see three panels of figures, three rows of figures. Can explain you why we used adaptive mesh here. You see that from top to bottom you have different times. Yep. And you have on the left the X plane, in the middle ZY plane, and on the right you have XY plane. So our initial configuration is that above let's say Y equal 0. If you look at the right panel, above you have magnetic field directed to the right, and in the bottom of this half of the box it's directed to the left.
Right. Okay.
So you create this current sheet in the middle.
This answer.
And you can see that something happens only near this midplane, right?
Right.
So there we refine the resolution to get the highest resolution. And we control this by determining the level of vorticity. So if there is some turbulence, it is refined to the highest possible resolution.
Right.
If nothing happens there, we keep the low resolution, because what's only important is that the inflow or the propagating waves which are leaving the box. So, so as you see, progressing in time from the top row to the bottom, we see that this structure is getting thicker. The structure we are seeing here is the absolute value of vorticity, which is simply the curve of velocity. We chose this to simply measure where the turbulence is generated. Right?
Yep.
So you can see that in the middle plane, for example, there are some bubbles of turbulent motions, and there are, with time, they are increasing the thickness of this region. And so we see that basically far from the current sheet, far from the midplane, there's no turbulence, and near the midplane, the turbulence is generated, and it's increasing the volume occupied by those fluctuations, turbulent
So if you waited long enough, would it fill the whole box?
Could be. I mean, there are other I would say factors which are also important. For example, resolution. If we have a limited resolution, it means that our numerical viscosity and resistivity will eat up the turbulent motions. You know, they will be dissipated.
Yeah.
And turned into heat. But since we use isothermal equations, it is dissipated very quickly, this heat.
Okay.
So also, as we know from the Lazar and Vishniak model, the biggest increase in the reconnection rate occurs when the resistivity is very small, and comparing to the, for example, motions of turbulence, you know, the injection scale, etc. So I would say that the dissipation regime or dissipation scale is far from the injection scale. Okay. So then we see this indeed the strongest increase in the reconnection rate. So so we can see that if we just allow a current sheet, elongated big current sheet in the box, and we inject some random noise, a velocity noise near this current sheet, the system will take over and start to generate through reconnection turbulence. Mm-hmm. And right, so without thinking about, okay, what is the exact process which generates this turbulence, we ask a different question: what are the properties of such turbulence? Is it compatible with some existing turbulent models, magnetized turbulent models, or not? Right. And since there are not many magnetized turbulent models existing, the one which is perfectly applied here is the Sridhar-Gordstein 1995 turbulent models of incompressible and strongly magnetized turbulence. And so this model predicts simply that the power spectrum of velocity fluctuations follows the one by Kolmogorov, even though the Kolmogorov turbulence is without magnetic field. The other thing which this model says, that the anisotropy, since we have magnetic field, strong, uniform large-scale magnetic field, the eddies, velocity eddies of fluctuations would be elongated if we go down to smaller scales. Okay. Because of the pressure anisotropy, the magnetic pressure contribution to the total pressure. So in the effect, on the contrary to the Kolmogorov model, where the fluctuations are isotropic, in this case, in the presence of magnetic field, we would have anisotropic structure of velocity. So, but before that, we wanted to see what is the amount of kinetic energy we can generate, and we have analyzed this, and we have shown this in figure 1 and 2. You can go back if you want. Yes, so we start with a very low level of velocity fluctuations. Indeed, it's as I said, this model is the collisional MHD simulation model. We solve MHD equations, isothermic MHD equations, and initially we create this large-scale current sheet, and we just inject random fluctuations of velocity field near the current sheet. And so you can see that in the beginning, the energy level comparing or normalized by the magnetic energy, total magnetic energy, is 10 to minus a few times 10 to minus 7. So it's orders of magnitude smaller than the amount of energy in the of magnetic energy in the system. Nevertheless, after some time, we see that the kinetic energy starts to grow after the initial decay due to the numerical dissipation. It starts to grow very fast. I estimated that this growth is like 10 to 4. So it's not exponential growth. Initially it is exponential growth, but then it is 10 to 4. And then it starts to saturate. So basically in in the presented models, we have increased by 3 orders of magnitude of the initial energy. Still, it is a fraction of the magnetic energy contained in the system, the whole system. So we can see that indeed the reconnection itself can generate turbulence, right? So the question is, we can see from the plots on page 7 that there are some structures, the eddy structure, there are some turbulent structure. We can measure the power spectrum, for example, of those structures. So if you could go down, slide down to, I think the next page after the page 7, maybe it's page 8.
Okay. There you go.
Oh no, so it's figure 5. So in the figure 5, we show spectra both for velocity fluctuations and on the left and on the right vorticity fluctuations, which are related. And so this yellow line at the large scale shows that initially we inject those small scale fluctuations, the random fluctuations, and relatively quick, we can see that the next light green curve is around t equal 0.5, shows that already the fluctuations take place at all scales, available scales. Simply k equal 1 means that we have fluctuations which have the wavelength equal to the size of the box. Of course, we cannot reach this wavelength.
Okay.
We reach a maximum like 2 times or half of this box, half of the box in the parallel direction fluctuations. So, but what's important that after some time, oftentimes this power spectrum saturates and reaches a slope compatible with cohomogorov one. So we can see that indeed this turbulence can be comparable to the Goldreich-Streethar model, which also predicted this k to minus 5/3 power slope. Right.
Yep.
So of course the interesting question is how from those small scales the fluctuations were created at large scale. Usually it's the opposite. Usually we inject turbulence at large scale and it propagates toward the smallest scales.
Right.
But well, we can leave this question open, you know, because in the later works, we try to answer those questions.
Okay.
Okay, so the power spectrum is one thing, and so another quantity which would like to compare to this Goldreich-Streethar model is the anisotropy. So if you slide down, how do we determine the anisotropy of the fluctuations? We use statistical tools which are called structure function. Structure function is just the difference between velocity. If you, it's sort of similar to correlation, but instead of the multiplication, we have the difference. We take, for example, the field, the velocity field, we shift it with a lag by some distance, and then we calculate the difference. We take the absolute value of this difference, and we calculate the average of this. Okay. So, but the one difference is that these plots, which are shown here on this page, show a two-dimensional structure function of velocity. Normally, we use one-dimensional, which is just a lag. But here we use two-dimensional because the structure function is determined by the local magnetic field orientation. So what you see as a L parallel means that the lag, the shift of the field was performed along the local magnetic field. And what is L perpendicular is a cross in the direction perpendicular to the local magnetic field. And from Gordreich-Sridhar model, we have a prediction that the eddy, velocity eddy, eddies are elongated along the magnetic field. Something which you would see, for example, in the middle left plot. But here we show a structure function isocontours for different cases, for different plasma beta numbers. So we have, for example, top row is for sound speed equal 0.5, which corresponds to plasma beta, I think 0.5 or 0.25. In the middle, we have beta equal plasma beta equal 2, and in the bottom we have plasma beta equal 32. Okay. So we can see that the anisotropy of those structures changes, and it's interesting that in some cases, like on the if you take a look into the right column, you see that the eddies are elongated in the perpendicular direction to the magnetic field, in contrast with the Gordreich-Sridhar model. Okay. Why this happens? We have a simple explanation. If you imagine a reconnection zone, a reconnection brings the magnetic flux together, reconnects it, and ejects this along the current sheet. And along the current sheet, you have a strong outflow, but magnetic field is, the direction of magnetic field in this outflow region is perpendicular to this outflow. So this means that the structure is deformed in the perpendicular direction to the local magnetic field. Okay. So, so we came to a conclusion that probably it means that we have two types of fluctuations. At small scale, the reconnection dominates, and it affects the statistics. And at large scale, when the reconnection does not play an essential role directly, the fluctuations have time to mix and tend to this classical Sridhar turbulence, right? Okay. Mm-hmm. So in the next page, we did analysis of what's the scaling of the anisotropy, and so basically you project this isocontours from the perpendicular direction to parallel direction using those isocontours. And you create such a curve which shows how the parallel direction is related to perpendicular one. And if this curve, as you can see in figure 7, is parallel to L parallel equal L perpendicular, it means that the structure is isotropic.
Right.
If it's more like proportional to perpendicular to 2/3, it means that it's anisotropic, and the scale relation follows the Goldreich-Streethar model.
Mm-hmm.
And what we can see, we have plenty of curves here for different time moments. So we can follow what happens with anisotropy when the system evolves. I would focus on the right panel in this figure, which corresponds to high beta plasma case, because it shows nicely that, for example, in the initial times, when the turbulence is not very well developed, everything is very close to the current sheet. The reconnection dominates those structures and anisotropy. But once we allow the turbulence to develop, it creates this volume and bigger each time. The statistics of the remainings of this more volume far from the current sheet starts to dominate. And if you look at the curve, which are the open circles, you can see that between 10 to minus 2 and 10 to minus 1 in the perpendicular scale, you have nice agreement of this relationship with the Goldreich-Streethar scaling, L perpendicular to 2/3, right?
Yep.
So, of course, at smaller scale, you have the dominance of numerical dissipation and numerical effects. At large scales, you don't have fluctuations resolved very well, so you have some different scalings as well. But with the limited resolution, we use up to 1024 resolution or in other sense, each length unit we divided in 1000 more or less cells. Yeah. You can see the creation or formation of this universal regime, inertial range, right?
Yep.
Which is the range between the injection scale and the dissipation scale. So to test this, that indeed the reconnection affects the statistics, we did a simple experiment. We stopped one of the models, okay, and we reorganized the magnetic field, the large-scale magnetic field, by simply inverting one of the halves. So you have the anti-parallel configuration. We separated this large-scale magnetic field from the smaller scale fluctuations, and then we inverted magnetic field, so you have this configuration, right? And we allowed the system to evolve. And what we could get, it's shown in figure 8, that we, for example, those circles, open circles and closed circles correspond to the simulation. It's called decaying turbulence.
Yep.
And they follow the Goldreich-Streethar anisotropy very well. While in the case of driven, driven by the mean of reconnection-driven turbulence, we still have this scaling a bit different because of this mixture of different, I would say, of different fluctuations which affect the purely turbulent fluctuations.
Cool.
So yes, we can say that we confirmed that reconnection can generate turbulence. From the measurements, we can see that this generation is more efficient if we have high resolution. Of course, if we have like larger Lundquist number, we can see that this turbulence, if let's say filtered from those reconnection fluctuations or from the effects of how reconnection affects the fluctuations at small scales, can follow nicely the Goldreich-Streethar model.
Mm-hmm.
Right?
Nice.
So, yeah. So I think, yeah, if I didn't remember anything, these are the main conclusions of this paper. Yeah, now the question is to answer how this self-generated turbulence affects the reconnection by itself.
Yeah, so that would be the next question.
Yes.
A research question.
Yes.
Okay, very cool. So if you look in your crystal ball, and of course this paper was published in 2017, and you've done other work since then, and other people have as well. So if you sort of look into your crystal ball, where do you see the field going over the next 5 years?
Well, we already did some work about what's the reason that those fluctuations are generated. The turbulence is generated in such an environment. We were testing different instabilities, imaged instabilities like Kelvin-Helmholtz instability and Turing mode instability.
Right.
So we can say that both are important. Of course, initially we don't have much shear, velocity shear in the system, but it's very quickly developing, and at some point the Kelvin-Helmholtz dominates the production of the eddies. Mm-hmm. So, of course, there are more interesting questions related. We could say, for example, some part of the work I've done related to turbulent reconnection is the particle acceleration. It's a promising mechanism for accelerating of charged particles in such environments, because because of the inflow of magnetic field toward the current sheet, we have perfect configuration for the first order Fermi process to take place, right. You know, and particles can bump up, down many times, yeah, and then gain energy and leave. So it would be also interesting to do such studies. Other studies I would include what I'm doing right now is, for example, to verify how the velocity shear affects the other instabilities like Turing mode instability as well. Okay. Because so far what we considered, we just determined that, okay, we have the current sheet, local current sheet, we determine the thickness of this current sheet, the longitudinal scale, we determine the local parameters, and we determine what is the growth rate of the instabilities. Okay. But of course, there are, I would say, even though there's a lot of papers during the last for 4 decades about Turing mode, there are missing like theoretical models, you know, theoretical predictions to maybe some configurations more complex than just the antiparamagnetic field in a slab configuration, for example. Yes. Yeah. Cool. All right. Future's bright. Lots of stuff. A lot of work. Yeah. Lots of stuff to do. All right. JG Ghosh, I want to thank you so much for describing your lovely paper with us. And thank everyone, you very much. No, you are so welcome. And everyone will thank you very much, and we'll see you on the next one. Bye-bye. Okay. See you.